Today's topic is the Coriolis Force. Have you ever had a dream of going on a trip beyond the Earth? Let's say you achieved that dream and became an astronaut in space. If you look down at the Earth's north pole from space, the Earth will be rapidly rotating anti-clockwise. Of course, we are usually not aware of that. However, there is a way to confirm that the Earth rotates without having to go out into space. One of the phenomena caused by the rotation of the Earth is the deflection of objects moving on the Earth. The hypothetical force that causes this phenomenon is called the Coriolis Force. The Coriolis Force appears because the Earth rotates. The perimeter of the sphere-shaped Earth is the longest at the equator and becomes shorter as the latitude increases. However, the Earth rotates once a day, regardless of latitude. For example, the rotation period at 30 degrees north and that at 60 degrees north are the same. Therefore, the speed of rotation is the fastest at the equator, and the speed slows down moving to a point of greater latitude, reaching zero at the South Pole and the North Pole. Let's say you're in Kampala. Kampala is the capital of Uganda, located near 0 degrees north and 30 degrees east. And let's say you kick a soccer ball from Kampala to Cairo. Cairo is the capital of Egypt, which is at a similar longitude to Kampala and passes 30 degrees north. Suppose that when you kick a ball, there is no frictional force or other force that affects the object other than the Coriolis force. Kampala, the launch point on the equator, rotates at a speed of about 1,670 km per hour. In addition to the launch speed, the soccer ball launched north has a speed of about 1,670 km per hour east at the same time. Meanwhile, Cairo, which is 30 degrees north, rotates at a speed of about 1,450 km per hour. The target point is moving eastward about 220 km per hour, slower than the launch point. Therefore, the fired object reaches a point further east than the aimed target point. When viewed from Kampala, the path of the fired object curves to the right of the northern direction that was initially targeted. This time, run the same experiment in Cairo at 30 degrees north and aim for St. Petersburg, which is at the same longitude. St. Petersburg is a Russian metropolitan city comparable to Moscow and is located at 60 degrees north with a rotation speed of about 840 km per hour. The difference in spin speed between the 2 points is about 610 km per hour, so the soccer ball you kick will fall even further to the right than when fired from the equator towards 30 degrees north. The degree to which the direction of motion is biased to the right increases as the latitude increases. Eventually, the degree to which an object's motion is biased is maximum at the north and south poles and zero at the equator. This bias occurs where objects move not only in the north, but also in different directions. Therefore, the direction of movement of the ball that the batter hits and flies over the baseball field in New York is also affected by the Coriolis force. The magnitude of the Coriolis force is related not only to latitude, but also to the speed of an object. The faster the speed, the greater the Coriolis force, and the Coriolis force does not appear on objects addressed on the surface. So, soccer balls sitting still on the playground are not affected by the Coriolis force, regardless of latitude. On the other hand, the Coriolis force causes the traveling direction of the moving object to be biased to the right in the northern hemisphere and to the left in the southern hemisphere. Therefore, an object fired south from 30 degrees south falls east of the target point. At this point, you might have this question: how am I going to observe a soccer ball kicked from Cairo to St. Petersburg? If the results of the thought experiment are hard to understand, there is another way, somewhat more sedentary. The Coriolis power can also be checked through a pendulum experiment conducted by French scientist Foucault at the Pantheon Temple in Paris in 1851. Foucault fixed one end of the 67-meter-long string to the ceiling and hung a 28 kilograms weight on the other end to swing. Finding that the pendulum's plane of oscillation rotates clockwise over time. This is related to the fact that when the pendulum moves, it is slightly tilted to the right of the moving direction due to the Coriolis Force. The Pantheon Temple in Paris is located at 49 degrees north, and if this pendulum experiment is conducted elsewhere on Earth, it would yield different results depending on the latitude. First of all, if the pendulum is swung in the east-west direction on the equator, the plane of oscillation would not rotate. The plane would rotate faster if the same experiment is conducted at a higher latitude than Paris. Finally, if this pendulum experiment is performed in the southern hemisphere, the pendulum would be biased to the left of the moving direction, and the pendulum's plane of oscillation would rotate anti-clockwise. Thanks for watching.